Hi, this is Professor Fernandez, and this is video 1 in lesson 12. The topic here is related rates, and there are a few things that I want to get done with this video. I've put a little agenda here on the right. Let me first say that because we are talking about related rates, I do encourage you to make sure you are comfortable with the chain rule. So that's covered in video 11.1 if you need a refresher. Okay, so what's the agenda here? So first, I want to do a quick little overview of related rates, and I've drawn in here a little bit of a setup that relates to this example. So I'll get to that in a minute. And then we'll actually walk through this example 4.1 as a first preliminary example of the concept of related rates. And then finally, we will talk about box 4.1, which is down here, and what's in there. Okay, so let's go ahead and do that first one, a quick overview of related rates. So in this example, which we'll read through in detail in a few minutes, what's going on here is that we have a square whose side length is increasing. And then the question is, how fast is the area changing? So I'm just going to go through this first of the three diagrams I've written. Let's say, for example, you have a square with side length 2. Then, the area is the square of 2, which gives us 4, so that's fine. What I want you to notice here is that this square has side length 2, so the side length is not increasing, it's constant. What if I change that assumption? What if instead of 2 being the side length, I now call the side length t, some variable? We can still write down the equation of the area of the square, right? So that's just side length squared, t squared. But now, because of the t there, I'm thinking t of as being a measure of time, the area of the square is changing, right? It's a function of t squared. So I could, for example, find its derivative, and I'm not going to get 0, as I would have gotten in this case, because the derivative of 4 is 0. So I've put down a little graph here, a little table, just to help you see this with numbers. So, if the side length is 2, then we're back to an area of 4, just like before. But if the side length is 3, we're increasing to an area of 9. So I want you to keep that in mind, right? The square's area is changing here because the side length is changing. Now, I know exactly how fast the area is changing because from t squared for the area, if I differentiate that, I get 2t. So in this case, I could say that the area is increasing linearly with slope 2. So that's a lot of information. That's very useful. So the last diagram here is, what if we, generalize this even further, right? We went from a square with a constant side length to one with a side length of t, and now we're looking at a square with a side length of x of t. In other words, we don't know the formula for the side length like we did over here, but we do know that it depends on time. So what would happen in that case? Well, so the area, as always, is still the square of the side length, x of t squared. But now to differentiate this, right, I need to use the chain rule. So that was the reason for very early on to talk about this video to review the chain rule. So how do I differentiate it using the chain rule? Well, I'm going to recognize something squared as the outer function. So I differentiate the outer function. X squared differentiates to 2x. And then I substitute in the inner function, and I multiply by its derivative. Okay. So the answer here is 2 times x of t times x prime of t. So that's my derivative. Now, let me show you another way you could have done this without having to carry around this x of t, all over the place, because it does make the differentiation a little cumbersome. So what you could have done is you could have said, well, look, this is a equals x squared, except that, x is not the variable. It is x of t. In other words, this is an implicit function of t. By that, I mean I don't know the formula. It's not like x of t is t squared or sine t. All I know is that x of t is a function of t. So if you start with this and you recognize that x is a function of t and so is a, then you could apply the chain rule in this Leibniz form. So this says that dA dt is dA dx times dx dt. This is the Leibniz version of the chain rule. And one nice way to remember the Leibniz version of the chain rule is that, if you treat this as a fraction bar, which it is not, and I talk about this in the textbook, but if you do, right, then it's easy to remember this multiplication as, oh, the dx's are canceled out, and you're left with dA dt. So that's one way to remember the Leibniz version of the chain rule. So if I go back then to this way of viewing the area just without having all the t's everywhere like they were here, then I can just differentiate here. So dA dx, that's pretty simple because a is x squared. I get 2x. And then I would multiply this by dx dt. And I get back the same rate of change equation that I got before, right? It just looks a little different. X prime of t really is dx dt. And the 2x here is the same here, and dA dt is the same here. So, either way you want to understand what we can do to find the derivative of the area here, works just as well. If you want to keep the x of t and a of t in here and do it that way, that works. That's a more what I would call traditional application of the chain rule. If you want to go the Leibniz route and you want to do it this way, that works as well. I will say that this is probably the fastest one and the one you'll see most often used in related rates problems. Okay, so I'm going to erase all of this stuff and then now go on to the second part of the agenda, which is the example. And you'll see that what we just did is going to come in very handy. So let's read through this example. It says the side length of a square is increasing at the constant rate of 0.1 feet per second. So first thing I want to do in a related rates problem is I want to draw a diagram, right? That's always going to help. So I know I'm dealing with a square and whose side length is increasing at a constant rate of 0.1 feet per second. How do I put that into my diagram? Well, I don't know the side length formula, right? So I'm going to call it x of t. So now this should be a little familiar from what we just did. And what I do know is that the side length is changing at the rate of 0.1 feet per second. So there I am mathematizing that, right? Notice a few things that I did. First of all, it's increasing. So the derivative should be positive, right? The x values are getting larger. And second of all, I've put in the units, feet per second. That's going to be useful because that also tells me what to write on the left-hand side, right? I'm calling x the side length and I'm calling t time. So I'm choosing variables already that are implicitly present in the information that's given in terms of the units. So feet is the measure here for the x variable, and then seconds is the measure for the time variable. So that's what I know so far from that sentence. And then how fast is the square's area changing? So we're talking here about how fast the area is changing. So I'm going to need a formula for that. So I have a square. So the area of a square is the side length squared. So that's my formula. How fast is it changing? So the question here is about dA dt. How fast is it changing when its side length, which we called x of t, is 1 foot, equals 1 foot. Okay. So at this point, I have mathematized the entire problem, right? If we step back, we look at the original prompt. It was written in English. There were no equations. And we now look at what we see before us, and we have the given information. We have the function that connects what we want to figure out to the information that we're given over here. And then we have the question that we want answered in mathematical form. So this is what makes this a related rates problem, right? The formula that we have come up with involves two variables, right? Effectively x of t and a. And when we differentiate this, like we just did, right, we're going to get 2x times dx dt. We did that a few minutes ago. You'll notice that this rate and this rate are related by an equation. So hence the notion of a related rates problem. So because we have already done the work to relate these rates using the chain rule or the Leibniz version of the chain rule, whichever one makes most sense to you, we can now pull in all the information we're given. So dx dt is 0.1 feet per second. We'll put that in there. And then we're asked to find dA dt when x is 1 foot. So we will put that in there. And then our formula tells us to find dA dt by multiplying all these numbers together. So we get 2 times 0.1, which gives us 0.2. And the last thing you want to do in a related rates problem is you want to include the units for whatever it is, whatever rate you're calculating, right? A is an area. We know that the units of an area are side length squared. we called x the side length. We're measuring x in feet. So feet squared is the numerator. And then t down here, we've measured that as seconds. So feet squared per second. So we would say dA dt, the area is changing at the rate of 0.2 feet squared per second. And that's our answer to the related rates problem. So let me finish this up by talking about, so we did this one, we did that one. Let's talk about this box 4.1. So I've included this in here just so you can see a little bit more of a guide for what I just did, so you don't have to sort of rewind the video and sort of take notes. This is not something that, this is more of a rule of thumb, if you will. It's not like a requirement that you set up a related rates problem this specific way, but in my experience, it does help. The first thing we did was to draw a diagram. So we also labeled changing quantities, right? We labeled the side length x of t. Then we wrote down in math what the rate the question asks for is and what the rates that the question gives are given. So we wrote down, for example, dx dt was 0.1 feet per second. And then at some point we asked, we said, the question asks us, what is dA dt? And then, like we said here, if the quantity is increasing, the rate should be positive. If it's decreasing, the rate should be negative. Had the question said, for example, the side length is decreasing at the rate of 0.1 feet per second, we would have put a negative sign in front of this 0.1. Okay, and then tip, use any units to provide, any units provided to determine what rates are given. So feet per second, that kind of tipped us off to say, okay, this is the side length per second. The problem also told us the side length is changing at 0.1 feet per second. So I say that here, feet per second is a rate of the form dx dt, where x is distance and t is time. All right, number 3, use your content knowledge. So we had to know that the area of a square is the square is the square of the side length, right? That was content knowledge from geometry, so that showed up in this problem. In other instances, you might need to use other content knowledge to relate the variables in the problem. We'll see that in subsequent videos. And then your diagram might help. We drew a square, so that certainly helps you think about the area of the square. Okay, and then the main thing here is that the equation you come up with should relate the variables that you've identified, right? We were given dx dt information. We wanted to find dA dt information. So we wanted a formula that connected a to x, and we found one. And then last step, find the related rates equation by differentiating your main equation. Oftentimes it's with respect to time or t, using either the Leibniz version of the chain rule or the chain rule in its original form. So I won't go over that again because we did that at the start of the video. So I'll just zoom in now and talk about very quickly, a quick little recap. So related rates, right? This is a great example right here. It is a calculus problem in which the objective is to relate 2 or more rates by some equation. Oftentimes that equation comes about from geometry. In this case, it had to do with the area of the square. How you actually get to that related rates equation, more often than not, it's using the Leibniz version of the chain rule, which is in this example this. But like we said earlier, you could use the original version of the chain rule. And then, this box 4.1, if you want to rewind, take a look at that. In my experience, again, this is a really helpful way to tackle related rates problems. They get much more complicated than the one we just talked about in this video. So down here, right, in the next video, 12.2, I'll start talking about more complicated related rates problems.